And that wire is used for the plants, so when the plants grow up, they can branch out and grow right on the wire. Well, one of the things I did, which kind of affected me later, is I got to this hill and I wiggled the wire and I saw this wave go down the wire, a long ways down the wire. It came back, small amount, and then the rest went on. I asked myself, what caused that wire, the speed of that wave on the wire? And what was it that had to do with this reflection here and that reflection? And so, you know, my boss didn't like it, but I was wiggling the wire in the field. And I thought, well, I'll go off to San Luis Obispo and study waves as part of electrical engineering. And that's what I did. I graduated having studied microwaves. And in microwaves, of course, it was the Cold War at the time. And everyone was concerned about identifying what kind of airplane's flying over, what kind of tank is on the battlefield. And so I worked at 100 gigahertz, actually it's all the way up to 100 gigahertz for radar testing. Now, why is 100 gigahertz important, do you think, for radar? You know, it's as you go up to the frequency of 100 gigahertz, the wavelength of the wave is only of the order like this. So when you have fine wavelengths, you can resolve the object shape very well because it gives high resolution. So the big push was around 100 gigahertz, and so that was to do with my first project. So the project is about how do you measure high frequencies when you have instruments that only measure, say, at the time, up to 22 gigahertz, fundamentally to 6 gigahertz. How do you make those measurements? Well, like a radio receiver, you take the incoming signal and you mix it, you send a low frequency signal into it, and you mix it in a nonlinear device. Nonlinear device, like a diode, scatters frequencies. It scatters harmonics out higher frequencies. And so what happens then is we feed the radio 6 gigahertz into this, and it creates all these harmonics, distortion. And way out here at the 18th harmonic, we mix that 18th harmonic with the incoming 110 gigahertz. It's close, and it goes out what's called an intermediate frequency at a low frequency, in this case 300 megahertz. And then you can measure them, because that IF is a mixture of local oscillator and signal, and we know the local oscillator, so we're able to find out what the signal is on the screen. So what if, instead of mixing on the 18th harmonic, we could multiply the frequency of the local oscillator so that we're only mixing on a much stronger scattered local oscillator effectively. That was my first project. It was develop this multiplier for a 110 gigahertz mixer. Now, I worked a lot with mechanical engineers on this, as you can tell. Looking at the machining that had to go into this, design of the connectors, the waveguide, and all that. And so, in that process, I was responsible for the development of this chain of electronics, which, to give you a sense of scale here, these substrates here were 127 microns thick. That's the PC board, effectively. It was 127 microns thick. You say, why is it so thin? Because at these frequencies, you need very good control over the electromagnetic fields. Anytime you have larger gaps, the fields fringe more and you have less control. I needed that control because the transistors in this circuit had negative gain. If you put it into a 50 ohm, what's a standard transmission system for electronics, 50 ohms, actually they were attenuators. So I had to get gain out of the system by designing all these complex capacitances and inductance, basically, to actually get what's called mismatch gain and actually make this thing amplify that multiplied signal. So it was beautiful. It looked great under a microscope. You could see the sapphire, the gold, and I was happy. And it worked. So at 110 gigahertz, we had 30 times sensitivity improvement compared to the best mixers in the world, which we produced. Right? We're the best. We have the best mixers in the world. This is 30 times better. Could that be a problem? Well, we'll see. It was. So, working in a team of about, it's me, a mechanical engineer, and then technicians that would do the bonding of all these gas pads and so forth. We put this into production, and then we hit an industry downturn. So what happens in industry downturn in industry? Well, they get together and they look at their expenses. And one person had the bright idea to say, we already have the best mixers on the planet. This is 30 times better, but it's already the best. And our field engineer knows how to sell it, and they're buying our mixers. So this other person said, yeah, we should cancel this project. And then they tell me, well, times are tough. We're going to have to cancel your project. And so there it went. So that was after about 4 years of work on this. Okay, so sometimes that happens in engineering. I'm just giving the projects that didn't work out. So the lesson there is as you take on projects in industry, always think about the economics of what you're working on and know the economic environment. Say, hey, if I'm working on something that's not in the core business, it's the advanced stuff out there, it might get dropped, right? And the company might focus more on the core businesses. So that was my lesson there, because when I came out of school, I said, okay, yeah, tell me what problem I need to solve, and I'll just go solve it. That's the way it was. But I should pay more attention to that. I would have known 6 months in advance that, hey, the project's going to go away. Right? So I went back to school. So, and you see a theme here about me going back to school, continuing education in engineering. It's not like when you graduate, you're done learning, right? You're going to be learning your whole life. So I went to Santa Barbara, came back, and at the time, there was a new kind of light source that came out. This is the laser light source that enabled the optical internet. How many here know what a distributed feedback laser is? Okay, not very many people do, actually. It's a device that's about 300 microns long. It's a laser. And the nice thing about this laser is it has what's called distributed mirror. Since distributed, it has a series of reflections that along the cavity add up to create a strong reflection in the opposite direction. It's called a Bragg effect in physics. So it turns out that this new laser could operate at a single frequency. All other lasers were at multiple frequencies, which caused problems with transmission. So it's a single frequency light source. We could put current modulation into it for the ones and zeros for the communication. And the nice thing about it is that this current level, unlike these big lasers that you've seen in the movies, it's only like 50 milliamps of current, so a very small amount of current could turn the laser on and off, ones and zeros, transmit information, right? But there's a problem. That beautiful modulation we would send on a 100-kilometer length, say between San Francisco and Sacramento, along this optical fiber, would come out to this horrible mess right here, this blob. So what happened? I had something beautiful here. We heard how good optical fiber is. Well, it turns out that there's chromatic dispersion in the fiber. What that means is that different wavelengths of light travel at different speeds. And so this light here actually has frequency content that's changing radically during the modulation, because the current modulation here is changing the cavity of the laser. It's changing the index refraction. And so the laser is changing. So that caused different frequencies. And I've seen this in the lab where I could see the frequencies at the far end, the beginning part of the slope. I can actually see the shift, like a track, the shift in that energy with those frequencies relative to pulse. So my first project was, coming back from the master's, was come up with an idea to measure the spectrum to find out what those frequencies are, right? So being a nascent inventor, I thought I want to invent something here. I'll use radio wave concepts like that microwave project, a local oscillator, mixing with the signal, and you get a representation of low frequency of that signal. How do you do with lasers? Well, the lasers turns out that they have something called phase noise. Phase noise is a departure from the cyclical nature of the electrical field. So electrical field's going up and down, and then there's some jitter on the phase. And after a while, you can't tell the difference if you know the waveform here, the phase. You don't know what the phase is there because it's completely decorrelated. There's no way you can predict the phase. So it's an independent local oscillator. I go, great, now this is kind of invention stage on a weekend. I said, now I have this independent local oscillator. How do I get spectrum out of it? This laser's being modulated. There's going to be modulation on both paths, so you're mixing modulation with modulation. Well, what you do is you turn it off half the time. And so I thought, well, if I turn it off half the time, when it's not modulated, there's a non-modulated state, a local oscillator state, and when it's modulated with the ones and zeros for communications, I get my modulated laser, and I can connect the two because that delay is the same as the on period of the switch. And so for the first time, this is the first time this ever happened in humanity, we can measure with a single laser the frequency modulation that was going on during modulation of that laser. Has everyone had Fourier theory and Bessel functions? So that's what describes this in communications. It turns out that the scattering of information follows a format that's related to what's called a Bessel function. It's actually squared. And so I could recognize quickly how much modulation was applied to that laser due to that current fluctuation. So I ran around the lab showing managers and the engineers, look, we can see this for the first time. So I was really excited about that. I asked the people in marketing, there's product marketing engineers, right? They do lots of things. One of the things is they assign a product number. Remember my first one got canceled? So it was 11980 local oscillator multiplier. So I asked them, I said, I want to get the 11980 into production. So can we call the new one 11980? And they say, yeah, we can do that. So it's 11980. That might have been pivotal in this project. The reason is by the time I went through school, got this design, we got hit by another recession. And the recession was bad, and they said, well, we don't have money to introduce the 11980. Because, again, I was always working on kind of the edge, not the core, kind of the emerging areas, and this laser stuff was emerging. And so they said, well, we don't have the money, it ought to be canceled. And so the VP said that he's not going to cancel my 11980 twice. And so I went forward. And actually today you can buy this on eBay if you wanted one. You know, it's been discontinued for many years, but there's perseverance, right? I use the same product number. Anyway, it's kind of a funny story. So I went back to school. And this time I went to Paris. Why did I go to Paris? A great city, of course, but it turned out there's a professor there that knew how to model systems with what's called quantum phase fluctuations. In other words, that laser phase is constantly moving with optical memory. In other words, optical memory just means that there's a delay in the system, the waves, optical delay. And so I went there because he knew a lot about this. So I come back, defended my dissertation. I speak French, by the way. I speak French. And went to work in labs in Palo Alto, Silicon Valley. Here. Just actually walking in that door right there. Now it's Tesla. Buildings are Tesla. So my project there was to create multicolor lasers. And what would you use multicolor lasers for? Any application? One was displays, right? Can I make a laser TV? I did some other stuff as part of this that I won't talk about, but I'll talk about it. I mean, this optical noise figure theory measurement, it succeeded, and now the methods that will be developed are used globally around the world for the internet. But I'll talk about, I will say it failed, so I'll talk about this other part. So, in the chart, which you all know, down here, the heavier, the bigger atoms, it's called the lanthanide series. This is a series of elements that are used a lot in like magnets, right, for cars and so forth. It turns out that they have properties that are really good for optics. And that property is it has an outer electron shells that protects the inner transitions. So there's in the electron orbitals, the electrons whose states are protected from outside influences. And that's key for magnetics and this application. So what if we didn't have visible lasers at the time, semiconductor compact lasers, gas lasers, big lasers, and so forth? What if we dope glass fiber with these rare earths that have these protected electronic shells and use that to make visible light? How do you do that? And by the way, that wasn't my idea. Other people had thought about doping these fibers, and they understood that they could have up conversion. So in that up conversion process, you take a low energy photon, invisible to the human eye. You absorb it in an atom. There's a whole bunch of atoms here. And you absorb it in each atom, and you raise the energy state of that atom. And then you absorb another photon, and you raise the energy once again. Now you have these atoms in an excited state, right? And that transition back to ground is visible because it has enough energy your eye can see it. And so I had a hand in this. That's my hand right there. That's kind of what the fiber looks like. There's a pump laser, semiconductor pump laser at a wavelength you can't see, and yet the fiber is purely visible because it's moving up this energy lattice, like moving up a ladder to higher energy states. So I was going to see what I could do there. Now you're all going to become laser designers now. So what does it take to make a laser? It's very simple. You need some optical gain, right? Well, we have that, right? We have these atoms in these excited states. They're ready to give their energy to the world. So we have that right here. We pump it with a laser. All you need is 2 mirrors. Once you have 2 mirrors, and the system is in an excited state, a little bit of spontaneous emission, just a little bit of random emission starts bouncing off the mirrors, and it creates a laser. And I have kind of a little simulation of that here. Pumping is going on. This is 100% mirror. This mirror is only 25%. And you see that one photon coming back is enough through the implication to double it and then create a lasing cycle. That's how laser works. And the frequency of that laser has to do with how long it takes the light to go back and forth on the mirrors. When you have a laser, what you'll see then is as you increase this pump power, in this case it could be 800 nanometers, which is beyond what the human eye can see, or 900 nanometers. At a certain point, you'll hit threshold, the system will engage in this stimulated emission through this process. You have a laser. And so that's what I did. And so in my system, I was using that praseodymium atom. It's distributed throughout the core of the fiber. I was pumping at 860 nanometers, which most people can't see. Turns out I can see it, which is strange, but no one else in the lab can see the light. It's a very deep, it's kind of like a black-red at that wavelength. It's like, if you can imagine a black-red color, that's what it looked like, 860. And so we pump up, and then that atom absorbs a little bit more light, more energy, and then I was aiming for the red color. For display, you need red color, right? Red, blue, green. So I got that, and it was quite a process. I had to clean the ends with boiling sulfuric acid. I had to polish the heck out of them. I polished the ends of the fiber and then put these mirrors on the ends. So coating in an evaporator, titanium dioxide and silicon dioxide to make this repeated mirror pattern. And from that repeated mirror pattern, you get effectively a mirror here, a mirror here. There's my optical fiber. That's going to provide the gain. There's my pump laser. You know, there literally could be 0.5 millimeter, right? The size of the pump laser. There's some optics in there. And that was my laser. And so I lined it up. The core was 1.7 microns. You can imagine, you know, sometimes when I misalign the laser, I could smell burning things in the lab, you know, because the intensity is really high. So my first laser didn't work. The end blew off. It turns out that you know, it just blew off the end. So I went through this process again. It took about 2 weeks, new fiber, and so forth. And then the second laser, it blew off the end of the facet. So right there, that whole end, that whole, all those little mirror things, they all blew off. And then I don't remember how many I did, but I had to change my process because it wasn't working. So finally, I improved the process, got the laser running at minus 196 degrees. Does anyone know why that temperature is important? It turns out, I know this because I did it, that's 77 Kelvin, which is the temperature of liquid nitrogen. So I literally had this fiber inside this copper little bathtub. And I got it to run at 100 at 77 Kelvin. Why 77 Kelvin? It's because these transitions at room temperature, they spread out. The thermal energy scatters the strength of that transition. So the single line here gets way spread out, and you lose gain. You lose the strength of that transition, called thermal broadening. And so once I got it working at these temperatures, I could understand how much pump light was being absorbed in the cavity, and I could optimize the cavity. Right? And so did that, and voila, my red laser turned out to be orange. It was the first time on the planet that's ever been achieved, and it was an accident. The accident was because the fiber length wasn't right, and the mirrors were detuned in frequency. And so it was an accident. So published this, you know, red and orange up conversion lasers equal in fiber, and it was published, you know, published it like, yes, according to theory, we should be able to do this, and we achieved our theory. When reality was, it was an industrial accident, and it worked. so it looked just like an orange. So anyway, that's a little story about sometimes luck happens, right? So went on, built the red, and then later developed the blue laser, and then interestingly, a blue and green laser. So now I have all the colors I need to build the laser projector, right, like the TV and stuff like that. And so the problem is that I was aware of progress being made in semiconductor lasers. These lasers, it has all that fiber in it. What if you could do it in a single chip, right, with a green laser? And so I saw that progress was being made. A guy got a Nobel Prize for this. And those compact lasers, I think, well, it's too expensive for that. There's a biotech group that was interested in the laser, and they wanted to replace their argon ion laser with my little laser here. And so here's the laser head that they were using before, the cooling system. This whole thing's the power supply. And my laser fit in the palm of your hand, right? It's powered by batteries. And they said, yes, of course we want to use it. And I said, you don't want to use my laser. And I said, why? Everyone at labs, does at labs, always tries to get us to use their technologies, even if they're no good. A lot of it's good. Okay. They always try to push it. Well, I told them, look, there's these new lasers coming along, and if you do my laser, you're going to get it in a couple of years. You want to use the new lasers. And they were happy for that ultimately. So I canceled my own project, right? because I was aware of what was going on elsewhere. You want to keep your customers happy. You don't want them to regret if they work with you. So I canceled my project, but the beautiful thing was I learned a lot about colors. When I see something like this, I can recognize, oh, that's a beautiful 543 nanometers, right? Or in California, Manhattan Beach, you walk along, you go, wow, I really admire this 602 nanometer light. It's really nice. Anyway, it's kind of weird. It's okay. So, canceled that. In the meantime, telecommunications is roaring, right? Everyone's talking about the internet and this and that. And so I thought, well, there's now a new laser that's swept in frequency. Remember the old lasers are single frequency? This new laser would sweep in frequency. Well, if it can sweep 5,000 gigahertz, we can use it as a local oscillator for an optical spectrum analyzer. Now, what does an optical spectrum analyzer do? It displays versus wavelength the energy of this light, the frequencies, the colors of the light. And so now I'm a manager. Here's my team. And the team is a mixture of various engineers from different professions, right? Different types of engineers. And one of the things that you'll learn out in the world is teamwork is essential. Always give credit. Give your colleagues more credit than you think they deserve, even if they're deserving of it. And they'll appreciate it for it, right? Because you learn to work together instead of competing, right, for the manager's attention. So I really pushed teamwork, and the team worked together. And actually, we built an optical spectrum analyzer, the first commercial one in the world, that used a laser as a local oscillator in a receiver. There's a laser, combines the signal, mixes on photodetectors, and you can see the difference between the classical technology in blue and the resolution we get with this laser-based approach. So that was great. With the optical internet, bandwidth was everything, getting more information down the pipes. So they started looking, well, let's not separate the lasers by, 100 gigahertz or 125 gigahertz. Let's separate them by 50 or 60 gigahertz. Actually, we really need a lot of stuff here. We're going to separate it by 6.25 gigahertz. That's known as ultra-dense wavelength division multiplexing. You don't hear about that today, right? And there's a reason. Because something happened along the way. Who remembers the telecom bust? That was a time when people like me, VCs, venture capitalists, would come to me and offer me millions of dollars. So just leave your job, form a company, we'll pay you. And say, well, I'm building my house right now. We'll take care of the house. And it was literally that way in Silicon Valley. There's so much money. And so all that money was being piled into this telecommunications for the internet. There's going to be buy dog food on the internet, all this stuff, right? They talk about back then. We do it now. But it collapsed, and that had to do with a delay in the economics of the internet caused that collapse. So you had 500,000 people lost their jobs, and all these companies going bankrupt, including WorldCom went bankrupt. So management gets together and says, well, Doug, you've been this photonic laser guy, you're leading these teams. There's no market out there for optical tests. There was so much equipment being returned on eBay that universities could buy anything they wanted that was new, literally new, on eBay. So anyway, there's no market. And so that project got discontinued. You can still buy it on eBay. And they said, well, you better find something else for your team. So, needed a new project. And this is the genesis of the laser mouse. I'm talking about how the laser mouse came about. So, I was told by management there's two areas that needed attention. One is printed circuit board tests. The customers are asking, how can they test their PC boards, the copper traces on them? That's a great question. You know, it depends on the situation. In one case, there was a talented engineer who wanted to be a researcher, and that's what he can't tell me. He wants to be a researcher. I said, well, you're not quite there yet. The training, the theoretics, and stuff like that. And so here's a case where I actually encouraged him to leave and to go to MIT, right? I encouraged him to go to MIT. And he says, well, most managers I've had always try to keep me. And here you are suggesting I actually leave your group. And I thought, given his goals, it'd be best. So there was a mutual situation. And then, so at the point where his project ended, Ali went off to MIT. He's doing quite well. He ended up in sort of venture capital, bioscience or something. So there was positive. Sometimes the economics hit, where you have no choice to let go of people you don't want to let go. That's always difficult. That's driven by company finances. And so there's a set deadline there that the HR imposes. Other times, like the statistician, I encouraged it. I said, okay, this is really not that's real. So we mutually agreed. He went off, became a millionaire. So.
Talking about where you report, like, do you have this various one member is orgy? Getting along well how big is
Yeah, if they're not contributing, that's a definite indicator. So they're not contributing, so you as a manager, your job is to try to find this person a place where they can contribute. And so you work with other organizations and so forth to do that. Other times you just forget, just leave. And it turned out in one case that I had two people, somehow they knew each other. One liked to whistle, and the other one couldn't stand whistling. And there's this thing that one tap on the table. And it was this weird interaction, so one of them had to go. And so one of them quit, right, because he couldn't stand the whistling. And 2 months later, he came back and his wife told me he wanted to return, but the position was gone. So I'd say when it's affecting productivity, it's time to go. When it's affecting the team, which is not affecting productivity, it's time to go. And then as a manager, we want to help them find the best track to go on even the organization. Having a good manager is important. I've always had good managers. But I've seen sometimes what happens with people, they have a bad manager and they hang around and it's not good. Yeah, that's a great question. Any other questions? One here.
Which project was the one that hurt you the most?
Yeah, I don't want to get the impression all my projects failed, by the way, but which one hurt the most? The first one, because as a new engineer, I'm thinking, I worked for 4 years on this project, and there it goes. That was the toughest. But I guess I could console myself that I learned a lot about microwaves in that time. I'm a far better microwave designer than I was originally. So that was the positive thing. But probably the first one was difficult. So you move on, right? You don't look in the rearview mirror. And I was always sort of on the edge of things, as some of you will be. You're kind of in the emerging areas, right? And so there's more risk when you're outside, your core business of your company. Yeah, if you want security, don't work on the emerging areas, stay with the core. Ultimately, as industry shifts, you'll be happy you went with the emerging area too. So. Yeah. All right. Well, thanks so much. This, by the way, this is the best questions I ever had. So my hats off to you. Thank you.